Where did the energy come? Well, somehow the energy that was transferred from these chemical reactions to the outside, which allowed the rocket to be pushed against the force of gravity, and which also allowed for the air underneath the rocket to receive a lot of thermal energy and get its temperature to rise. If there is such a thing as conservation of energy, that means that energy must have been somewhere. Where was that energy? What we're going to propose is that that energy was in a form that we're going to call potential. In other words, it was sort of like stored, all right? So let's look at this diagram here, all right? And tell you what I'm going to do is I'm going to go back here to my paper because I want to doodle here. Actually, I think we can do it here. All right. So let me get my, again, my marker here. Let's get my pen. And what we're going to do is let's look at the diagram on the left. Okay. Imagine that you have a ball that is moving, in this case, from left to right at a certain speed. And of course, that ball has a certain mass. All right. Notice that at that point, because there is nothing really opposing it, that ball is carrying purely, essentially, kinetic energy. You can see it here, that bar there. It's a lot of kinetic energy that it carries. But then what happens is, as it reaches that slope over here, hold on a second. As it reaches this slope here, as you can imagine, as it starts climbing, it slows down. Why does it slow down? Because now there is gravity opposing it, right? Notice that because it is slowing down, that means your kinetic energy is decreasing. And another form of energy, PE, which is the potential energy, is now increasing. When the ball reaches the maximum elevation that it can reach, for a brief instant, that ball has stopped moving. That means that its kinetic energy is essentially almost zero. But it got there somehow, which means whatever kinetic energy it started with has to have gone somewhere, because we said energy has to be conserved. Well, where it went was it became potential energy, all right? Potential energy. This is the second, form of energy that we can study. Now, what does this energy depend on? Well, notice that at this precise instant in time, that ball that we have in here is at the maximum height that it can go against the force of gravity. Gravity is opposing the ability of that ball to go up. And so what happened was that in order for that ball to get there, energy had to be transferred into that ball so that it could oppose this force of gravity. That energy that was transferred into the ball, which came originally as kinetic energy, is now stored in there because that ball wants to fall back down, right? When the ball falls down, we say that all that potential energy, that energy that is stored in there, that was put in there by making the ball essentially oppose the force of gravity, that energy is now potential. But as the ball begins to fall back down, what happens is, as you can see, the potential energy decreases, because now as the ball moves again, it is converting that back into kinetic energy. So you can see that there's an interplay between these, okay? Remember, that we said that energy is either exerted by or transferred into my system in order to oppose a natural attraction. So in this case, what we did was we essentially pulled this ball away from the center of gravity of the Earth, which means you needed energy in there. And therefore, the higher this ball had been able to go, the more the potential energy that it would have had. Okay? Now, since the let me go ahead and erase some of these scribblings here so that I don't get in your way. So I want to show you something essentially. All right. What we're going to say is essentially that the energy that would be required to move a system against a fundamental force from a zero reference point to its current position, okay, that is what we call the potential energy. All right. Now, notice that if we had started with the ball in a stationary position and we had pushed it, we had exerted a force that moved it over a certain distance at a certain velocity, the kinetic energy would have been the energy that was transferred into the ball to achieve that speed over that distance. The potential energy is kind of like the reverse, is what would be the energy that we require for me to take an object or a system and move it against a fundamental force starting at a zero reference point up to its current position, all right? So with that in mind, remember, kinetic energy is the energy that's related to the motion of an object. In our case, molecules and atoms and stuff like that have different kinds of motion, and therefore they have a certain amount of kinetic energy. We're going to call it thermal energy, and we'll get a window into it by measuring the temperature of our system. Now, potential energy essentially has to do with what is the relative position of my system with respect to an attractive force. Am I close to it, in other words, in favor of it, or am I away from it, in other words, kind of like not in favor of that attractive force? And that's what potential energy is all about. So let's go back to our rocket. We ask, where did the energy come from? Well, the idea is that the chemicals that are stored in these rockets, for example, we have, in this case, you can see the reactions here. You can see there's hydrogen and there's oxygen. And then there's also aluminum and ammonium perchlorate. Those substances, we're going to say, they have, let's say, just like the steel ball that was kind of going up that slope, they have a certain amount of potential energy. It has to do with how those atoms are positioned with respect to each other, how the atoms are placed in these molecules, how for example, the ammonium and perchlorate ions are interacting with each other. That's an ionic compound, right? So it would have some kind of electrostatic attraction in there. But also remember, within the polyatomic ions themselves, the ammonium and the perchlorate, those atoms also have some interactions between them. All of that essentially tells you these things have some kind of potential energy in there that has to do with the forces of attraction between atoms and between molecules. When I carry out the chemical reaction, I end up with other substances. Excuse me, let me have some water. We're going to say that these new substances have a different amount of potential energy. They're arranged differently. They have different kinds of interactions between the atoms. And so there is essentially a change. There is a difference in the potential energy between the reactants and the products. Remember, when you go from reactants to products, there's going to be a difference in potential energy. So we had to ask the question, well, where is the difference going to go? Because energy cannot be destroyed. Well, that difference is what gets converted into the work that pushes the rocket up and the heat that causes the air underneath to warm up and increase its temperature. And that's how things work in here. All right. So again, let me erase all these things here. Go to the next slide here and show you essentially what is going on. Okay. So a chemical reaction is going to happen in this system. All right. That chemical reaction is going to do a couple of things, right? One of them is it's going to produce some gases that are going to, I'm sorry, it's going to produce some gases that are going to, oops, this thing is not working for me, that are going to expand and push out here. And the force of those expanding gases is going to be work that pushes the rocket up. Again, where did that energy come from? Well, it came because the potential energy that was contained in the reactants was different than the potential energy that was contained in the products. And that difference in energy is what got converted into the energy that created the work to push up the rocket, and also the heat that got transferred into the air around to raise its temperature. We're kind of like simplifying things. You'll notice there's other things here. For example, there is light, right? There's flames in here. That's light that is also visible. That's also energy. There's also air that vibrates out and you hear a tremendous noise, when the rocket lifts off. So that's also another way of energy. So not all the potential energy that was stored in the fuel molecules gets converted into the kinetic energy, the work of moving the rocket, or the heat that is changing the temperature underneath. Some of it is being changed into other forms, okay? So essentially, let's go ahead and come back here. Let me erase these things. And let's go and summarize here. So this is a summary of what we just talked about. We said energy is essentially the capacity to do work. What does work mean? It means moving a system against a fundamental force in nature. In our case, mainly it's going to be either gravity or electromagnetic force. There are two kinds of energy, kinetic and potential. Kinetic energy is that which is related to the motion of particles. Potential energy is due to the position of the particles with respect to a force. But since the force we're talking about is the attractions between atoms and between molecules, really a lot of that has to do with the composition of the substance. You know, what kinds of atoms, what kinds of molecules make up that substance. So we could say potential energy is due to composition, all right? Now, with kinetic energy, of course, there's many different kinds of motions. The one we're interested in is thermal energy. We said this is due to the motion of the particles that make up my substance, whether it's, moving of the particles around, rotation, vibration, and it is all associated with temperature because that's what we use to kind of look at it. Potential energy, as we said, has to do with the positions of the electrons and nuclei in atoms and molecules. And because of that, we sometimes refer to it simply as chemical energy. Not that all potential energy is chemical, but definitely what we call chemical energy is a subset of all the different kinds of potential energies that there are. Now, earlier, I mentioned that in the fuel tank of the rocket, right, the substances that are there are chemicals, and what they're doing is they are essentially changing in their potential energy when they convert from reactants to products. Let's do that on a graph here. Okay, let's consider a reaction between reactants A plus B converted into products C plus D. And I'll tell you what that middle symbol is in a moment, okay? Let's say that you have a reaction where as you go from left to right, as you track the progress of the reaction, let me use my highlighter again here. As you track the progress of the reaction and you measure the potential energy, what you see here is that the reactants started out with a higher potential energy than the products. This is what happened with the fuel in the rocket. The reactants had a higher potential energy than the products. And that means that as you go here, you're going to have essentially a change of energy that is negative. In other words, the overall change in energy here is going to be negative. Where does that energy go? Well, like I said, you cannot destroy it. So what's going to happen is as the reaction progresses, that energy that is quote unquote lost is actually transferred to the surroundings. We call this an exothermic process. And by the way, most chemical reactions proceed with this little peak that you see here, right? In other words, they don't go straight from reactants to products. They don't go straight that way, all right? They simply go to this peak over here. And what that is the activation energy. Every reaction requires like an initial investment or input of energy to initiate the reaction. Somewhere in the progress of that reaction, there is something in here that it has different names. It's called sometimes the activated complex, sometimes it's called the transition state. It's kind of like a state in which the reactants and the products are about to carry out the reaction. The atoms are about to join, or the atoms are about to split, or the molecules are about to, bounce off each other. Whatever the case is, it's kind of like a kind of an in-between state, and we call it either the transition state or the activated complex. All right. So I just wanted to show you that because a typical energy diagram looks like this. Now, there are other cases where the reactants actually have a lower initial energy than the products. And in this case, we call this an endothermic reaction. Endo for into. So in other words, in order for the reaction to happen, the reactants, we're going to have to make up this difference in energy. How? Well, what they do is they take the energy from the surroundings. And so the surrounding has a different temperature and it provides energy so that the reactants can change into the products over here. We call that an endothermic reaction. All right. Let me show you some cool examples here. All right. And let me erase all this here for a moment. Okay, I got here a little interesting picture on the left. Okay, so here is a matchstick that's been lit up, and there's two thermometers, or actually thermal probes, and they're connected to a digital display you can see here on the bottom, right? Notice the one on the left reads 23.0 degrees. This one reads 31.0 degrees. In other words, the temperature that this thermometer is registering is higher than the one that this thermometer is registering. Why? Well, because it's closer to the flame. But how is the temperature of the thermometer increasing? Well, remember, the thermometer, all it does is it registers the average thermal energy of the particles that are around it, which means the air around the tip of the thermometer there. If the temperature is higher there, that means that those particles of air there are receiving an input of energy that is causing them to move, vibrate, or rotate faster. They have more kinetic energy. So what that tells me is that this process of generating this flame here must be exothermic. Notice that what I'm measuring is not what happens in the system itself, in other words, the burning matchstick, but in its surroundings, the air particles around it. Okay, let's say I went to Ben and Jerry's, or I don't know, one of these places, Haagen-Dazs or whatever. I brought myself a little ice cream with some sprinkles. Again, notice that the thermometer that is closer to it has a lower temperature than the one that is farther away from it. Why is that? Well, it must mean that the air particles around this thermometer are having less motion, less kinetic energy, and that's why the temperature is registering a lower value. Now, what is happening to that energy? Well, what's happening is that the process of the ice cream melting here is absorbing energy, and it's absorbing it from the air around, and that's why the air around is losing, quote unquote, kinetic energy, and that's why the thermometer is registering a lower temperature, and that would be an endothermic process. Again, notice that we don't really measure the energy change within the system itself. What we're registering is the temperature of the surroundings, okay? Okay, so let me do this. Let me erase these things. And let me make a little stop here for a moment and see if anybody has any questions, all right? Any questions here? Just, I mean, other than, you know, technical stuff, I know some of you might have an issue with technicalities, but don't worry, the lecture's being recorded so you can see it later. Does anybody have any questions so far? Okay, I don't see anything here. I guess not. Well, one of two things, either you guys are asleep or I'm doing a fantastic job. Hey, my choice, right? Okay, let's go back to our screen again. And let's wrap it up. I'm about to finish here. Okay, we were here. Back to our little presentation here. And here goes. Okay, so just like with matter, we measure the amount of mass in grams or kilograms, and we measure the amount of space occupied in liters or things like that. Well, it turns out that in these cases, we're also going to have to okay, here we go. We have units of energy. Okay, now we'll talk a little more about this when we talk in the next lecture, which, like I said, it may be a pre-recorded one that I'll have you watch. Let's talk about the amount of kinetic energy. Remember, kinetic energy is due to the motion of particles. And we have the formula, kinetic energy equals 1/2 mv squared, in other words, the mass times the velocity squared. Now, in order for us to line up with the International System of Measurement, we have to use the proper units. So kilograms are going to be the unit of mass here, not grams. And velocity is not going to be miles per hour. It's going to be meters per second. So in other words, the units of energy would be kilograms times meters squared per second squared. That's a mouthful, isn't it? Well, it turns out that, as we'll see in the next lecture, when we talk about the studies of heat transfer, it turns out that once people realized that work and heat were kind of like two faces of the coin, in other words, two different ways in which energy could be transferred. In the field of studies of heat, there was a unit called a joule. And it turns out that you can say that a joule is the amount of energy required to move a 1 kilogram mass over a distance of 1 meter. And so 1 joule equals 1 kilogram times meter squared per second squared. Now, notice that at this point, since we're talking about kinetic energy, in other words, about work, a joule is a unit of work. But what it's going to do is it's also going to allow us to think about heat when we use the units of joule. I put something in here just so you can see. If you want to read this about this later on in your book, okay, just want to make you aware that in our society, we don't use joules here in America. We use usually, watts and kilowatts, hours, and stuff like that. I'm going to let you read in your textbook about that, okay? I'll let you look it up. I'm not interested in conversions here and this kind of thing. I'm more interested in us knowing what these units of energy are. So let's go ahead and go to the next slide here. Okay. So scientists were also studying what happens when, for example, I change the temperature of a particular object. And how can I relate that change in temperature to amounts of energy? And so one of the definitions that came up was the calorie, small c-A-L. This is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. All right. Now, of course, you could also talk about kilocalories or kcals. That would be the energy required to raise the temperature of 1 kilogram of water by 1 degree Celsius, or 1,000 grams, right? So 1 kilocalorie would be 1,000 calories. When you look at a food package, for example, and you see the, as we are fond of looking at the calorie count, right? One of the things that we'll see, of course, is we'll look at the calories. And it says here, calories in this package, I think it's the cereal bar or something like that. 130 calories per serving. Now notice something important here, and that is that this is in units of calories with a uppercase or capital C, all right? This is what's called a food calorie. And a food calorie is 1,000 calories as we define them here. In other words, a food calorie is a kcal. So when it says there that that package had 130 calories per serving, that unit of calories represents, kcals in our lingo here that we've been using. Let's see if I can get this guy here. Okay. So please be aware of that. That's a very big difference. And again, if you're into that, you'll notice some of the conversions. For example, 1 calorie equals 4.184 joules. In other words, if we wanted to know what is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius, in joules, which is the units we use, it would be 4.184 joules. All right. Here are other conversions, for example, the kilowatt hours, the food calories and whatever. Again, you can look at this later. We're not going to be doing conversions problems here with this, but you probably will in your homework. So be aware of this table here, right? Okay, once more. During any process, energy can be converted from one form to another, but never created or destroyed. So, this is something that's going to evolve into what we're going to be calling the first law of thermodynamics, all right? So it requires that during any process, whatever energy change the system experiences will have to be counteracted by a similar change in the surroundings. In other words, whatever change happens in the surroundings and whatever change happens in the system, they have to essentially offset, counterbalance each other, because the universe never changes energy. The total energy of the universe is constant, okay? Don't forget, this symbol, this triangle, is the Greek letter delta that represents change. And remember, it's always final minus initial, okay? Don't change the sign on it. It's always final minus initial, meaning that a delta something can be positive or it can be negative. All right. So again, let me those things so we can go to the next one. Okay, so here's my rocket. All right, what is the total energy of this system? You know what? We have to, let's define that. Let's say that we're going to talk about what's called the internal energy. This is the total energy of all the particles that make up the system. Kinetic energies, potential energies. In some textbooks, they use the letter U to represent it. In some other ones, they use the letter E, both in uppercase typically. All right. Now, here's what's important. We are usually not going to be able to measure the actual amount of energy. There's no way to measure all these potential and kinetic energies for all the particles that make up the system. We cannot calculate that absolute value. So typically, what we do is we measure the change in the total internal energy, because that change only depends on how much energy you had at the beginning and how much you had at the end. And that's because the internal energy of a system is something called a state function. It's a mathematical function that depends only on what were the initial and final conditions, not on the process you use. In other words, what matters is where you started and where you finished, regardless of how you got from start to finish. So we would say that the internal energy, delta E or delta U, would simply be the difference between the final energy and the initial energy of the system. Let me show you how this works in terms of what a state function is. Here's an illustration for it. Let's say that you have a mountain here, okay, and it's about 10,000 feet to the peak. And there are two trails that go into it, all right? One of these trails, all right, is a long and winding trail. You can see it here. It takes about 12 miles of hiking to get there. And then there's another one that is kind of very short. It's only 5 miles, but it's also very steep. All right. Notice that regardless of which trail you used, right, when you reach the top, you're going to be at 10,000 feet above the base camp. In other words, the distance from the base to the peak of the mountain only depends in the difference in elevation between the peak and the base. Now, of course, the trip itself, the hike itself will be different, because if you took path A, you would have traveled 12 miles. If you took path B, you would have traveled or hiked 5 miles. You probably would have had a more leisurely hike if you had taken path A, because it's not as steep, but you would have probably taken a little longer to get there. It doesn't matter. When we talk about the height, regardless of which path you took, you went from 0 to 10,000, and so the difference in elevation was 10,000 feet, regardless of which path you took. That is what a state function is, all right? Now, we can do this kind of representation with energy diagrams, all right? We can use, for example, this kind of graphic here, all right? Let's say that I have a reaction where I have, for example, carbon and oxygen gas, energy diagrams. So what I'm doing here is I'm showing a reaction, but instead of showing it like, reactants, arrow, products, I'm showing them at their energy levels. So you can see here in this top part here that I could take, starting with carbon and oxygen and making carbon dioxide, you can see that the energy of the reactants in that case is higher than the energy of the products. That means that the change in energy of this system is going to be negative. In other words, final minus initial is a negative number. Now, if I were going in the opposite direction, if I were to start with the carbon dioxide and I were to decompose it into carbon and oxygen, you can see in that case, final, which is the products, minus initial, which is reactants, gives you a positive value here. All right. So you're sometimes going to see these diagrams where they show you the reactants and products not in a straight line as an equation, right? So they show it to you in the form of this. So for example, in this case, if I were to go back here, where is my control here? In a second. So for example, in this case, let's say the reaction were CO2 changing into carbon and oxygen gas, right? So that's the way we're used to writing a chemical equation. But notice that in this case, what we are doing is we're representing it according to the relative internal energies of these two sets of species, okay? So all I'm saying is this is what's called an energy diagram. So please get used to working with these, all right? Now let's do the following. Let's look back at our set of energy exchanges. So whenever I have something like this happening, it's obvious that there is a change of energy. Because of conservation of energy, whether this was a positive or a negative change in energy, in other words, whether the energy decreased or whether it increased, that energy did not disappear. It did not get destroyed. It had to go somewhere or it came from somewhere. Essentially, what we're saying is that in chemistry, we say that energy will be exchanged between the system and the surroundings in two ways, heat or work. We're going to use the symbols Q for heat and W for work. Now, unlike some texts and some authors, I prefer to keep these two letters in lowercase. So not capital Q, not capital W. Why? Because these are not state functions. In other words, because each of these represents a transfer of energy, not a content of energy, how they are transferred in a process is not always the same. Therefore, these are not functions of state. However, because of conservation of energy, if a system undergoes any kind of energy change with the surroundings, it has to have been in one of two forms, either heat or work. And that is where we get what we call the first law of thermodynamics. Delta E equals Q plus W. All right. Now let's look at some scenarios. We have to set up some conventions. Let's start. I'm going to start here from the bottom. Let's look at here. Let's say that delta E is positive. Well, what that means is that energy is flowing into the system. In other words, the system started with less energy that it ended up with, and therefore delta E, final minus initial, is a positive number. If it is negative, it means that energy went out of the system. In other words, the final energy was less than the initial energy, and therefore when you subtract those, final minus initial, you get a negative value. Okay, so that probably should be fairly obvious. All right, now let's look at heat. Again, if heat represents the transfer of thermal energy, if you have a positive value, right, what that means is that the system gained thermal energy. Thermal energy was transferred from the surroundings into the system, and therefore we have a positive sign on heat. If the system transfer heat out to the surroundings, then that means that the system lost, quote unquote, thermal energy, and so it has a negative sign. Remember, we don't calculate the heat transfer as a final minus initial because, like we said, heat and work are not state functions. We're going to have to figure out a way of calculating what is the heat that is transferred in a process. Okay? Now let's look at work. This one's a little bit tricky here. And the reason is that the definitions here on this table might not be make a lot of sense. But think about it this way. The question you're going to ask is energy going from the system to the surroundings or from to the surroundings, to the system. All right. So let's say that work, in other words, energy of work is being done on the system. That means the surroundings are transferring work energy to the system. It's almost as if this energy in the system has increased, and that's why you have a positive sign. Okay, so positive W means that the surroundings are doing work on the system. Negative work means pretty much asking the question, which way is energy going? Is energy going from the system to the surroundings or the surroundings to the system? If energy is going from the system to the surroundings, just like for heat, it was negative, just like for total energy is negative, then the same way work is also negative. This is energy that the system is exerting out into the surroundings. So work is going to have a negative value here. Okay,